So a reminder that we will be using the extra lectures next week and 2 weeks after, or 1 week, 2 weeks later. The solutions for the midterm are posted. Should be up already. And we have one more session for you to get your midterms back, and that is on Monday, 5 to 7, in a big lecture hall. I'm sorry about the mess with the midterm pickup last time. It's an RCH 101 that's also posted on the course website. What I need you to remember for today's lecture is up here on the board for you. Not so much the first one, second one, but the third one for sure. A tangential of an object or a circumference of an object that is spinning is equal to alpha r. The torque is equal to r cross f. From that, we need this, rf perpendicular. And f net equals ma becomes torque equals I alpha. One last thing is that I about a given axis is equal to I about a center of mass plus the mass of the object multiplied by d squared. So we'll do probably 2 examples today. Your assignment is, both assignments, 6 and 7 are ready. One is due on Tuesday, and it's coming Tuesday. One is due the Tuesday after. And we should have about 3 after that. 1 statics, 1 waves, and 1 superharmonic motion. Yes?
How come it says it's due 11:59 a.m.?
Say again?
It says it's due 11:59 a.m.
No, it should be PM. Yeah, we'll fix that up. Both of them or just number 7?
I think both of them.
Both of them? Yeah, we'll fix them both up. They should be at midnight. The quiz on this coming Monday, the quiz will be pretty much what we covered this week. All right, so you have a pulley, 2 masses and a pulley, and the moment of inertia of the pulley is given to you. The rope goes around one mass all the way around to the other mass, and this mass falls. Find the tension and find A. So what I'd like you to do is draw the free body diagrams and then write down the equations of motion and see what you could do with the solution. Review. It's from last lecture. It's the distance between the 2 axes in the parallel axis theorem. It's from Wednesday's lecture. Okay, so let's do this together. So we have M2G and tension T. Here we've got M1, I got tension T. And the pulley also should have a free body diagram because now it has a moment of inertia. Okay? Well, the first one is easy for M1. T equals MA. And for this guy, for M2, sum of the forces in the y direction equal to MAY. Then the tension T plus M2G equals to M2A. And picking down is positive, so M2G minus T equals to M2A. And we go to the pulley. What happens in the pulley, guys? We have now, for the pulley, we don't say sum F equal MA because the pulley is not translating. It's not running away from us. It's going to rotate, spin about the axis center of symmetry. So the appropriate thing to say would not be F equals MA, be torque equals I alpha. So for the pulley, sum of the torques is equal to I alpha. Sum of the torques is equal to I alpha, and sum of the torques about O, that's the center of the pulley, is equal to I alpha. What exerts torques about the center of the pulley? We have tension and tension, right? How do you see that? Well, best thing to do is to draw the moment arm, and if you recall, the moment arm is the perpendicular distance between a pivot and a force. It's really the effective distance over which the force will act. You could think of it that way if you want, but perpendicular distance from the force to the pivot. And okay, so sum of the torques is equal to, say, this is going to be 1 and this is 2. So it's equal to what? Tau 1 plus tau 2 equal to I alpha. As we said last time, guys, when it comes to forces acting in a given direction, we have to, after we write down our either scalar or vector equation in the format that we are using, we have to pick a positive direction and write down the magnitudes. Okay? In the case of forces, obviously we picked this is positive and we picked down as positive. However, for torques, if you recall, very important to remember that up and down don't matter anymore. Okay? So these forces, what do you pick as positive and negative? We're not concerned about the direction in which the force points. This is a rotational problem. The sign of positive and negative should be picked upon based upon a direction of rotation. So typically what you do, you could say because torque is a vector, you could pick a vector out or into the board to be positive, but for our purposes, we'll just use a squiggly kind of rotational vector like that and maybe pick this to be positive. But what's important to remember, guys, is that when it comes to torques, we don't look at what the force direction is. It doesn't matter if it's up or down. All we care about is in which direction is that force going to try to spin us if it has its way. That's all that matters. So one would be pointing that way, pick that way to be positive. So minus tau 1 plus tau 2 is equal to I alpha. Okay? Now what are these torques equal to? Well, the torque is equal to, look over there, the one definition that I want is RF perpendicular, so that's just R times T. So negative RT plus RT, tension on both sides, equals to I alpha. All right? Are we good? Forces, pulleys, masses, we're done. What? No. Why would it be 0? It's a heavy pulley, it has a moment of inertia. What's wrong with you? It has a moment of inertia, I. You did not put your hand up. I will kick you out of the class next time. I will, Kevin. Don't test me. Or test me, please. Piss me off, man. You won't be going off for long, for like 3 or 4 minutes. You go cool off or something and come back. So what was here?
Is this assuming that the string doesn't slide on the pulley?
It doesn't slide, no. What?
Isn't there a force of friction to consider?
No friction. It's a frictionless pulley. Yeah, wait your turn. What? Moments of inertia? What the hell? One pulley, man. What are you talking about? Ugh. What? What the hell? What? Kevin, what do you want? Yeah, so? Which cancels out? Yeah, okay, you guys got it. What's wrong with this picture? What's going on? Guys, please close your laptops. If you're not, there's no laptops open except for yours, but that's fine. I know what you're up to. Avi, don't look so distraught, okay? If you could look any more in distress, I'd be, start to worry. She's like, what the hell? All right, so guys, please pay attention here. It looks nice and sweet and smooth, got all, bells and whistles, vectors and some notation. Even it has the positive and negative directions on it, right? But something is seriously wrong in that if you look at this equation here, guys, if the two tensions are the same, what is it saying? That plus that equals to 0. When is that 0? I mean, in principle, when are the tensions equal? If one of two things happens, right? If alpha is 0, the system is not moving, then yeah, the tension will be the same, right? Or if I is 0, what does I 0 mean? Massless pulley. That is what we have done so far in the course. Anytime we had a pulley, it was massless, so the tensions were equal. But if the pulley has a moment of inertia, it has mass basically, and the pulley accelerates, then these cannot be equal. So we have to say RT1 or RT1, yeah? T2. We have to relabel all the tensions in the problem. This guy will be T1, this is T2, and this is T1, and this is T2. All right, so now we have equation 1, equation 2, and equation 3. How many unknowns do you have now? T1, T2, A, and alpha. So 4 unknowns. How do you deal with 4 unknowns? Well, you just substitute, okay? I need 4 equations. What's the 4th equation? Where do I get the 4th equation from? Remember that A is the A here. That is the same as the A there. Same as the A on the pulley as the pulley spins. And from there, that number is equal to the acceleration of an object at the edge of a pulley, object rotating at angular acceleration alpha at a distance r from the center is given by A equals alpha r. So this is 3 and this is 4. 4 says A equals to alpha r. Okay. So we have 4 equations, 4 unknowns. How you do it is up to you. Find A, please. I will give you a little tip though, guys. If you don't want to use linear algebra and reduce matrices, which is really a waste of time in this case, because there's 4 equations for us, substitution is the best way to do it. How would you, normally, how would you substitute variables? You have to, what you're trying to do is replace all the variables with 1. The best way to do it is to look for the equation that has most of those variables in it, okay? And in this case, we have one mass moving this way, one mass moving that way, and we have the pulley that kind of combines the motion of both masses. The pulley is controlled by the tension that controls that, and the tension, so the pulley, in the equation of motion of the pulley, we already have the tension that controls M1, the tension that controls M2, and within that equation we also have one of the variables that are related by A equals alpha r, rotation to translation. Okay, so we have in this equation all the variables that we need. So my advice to you is if you have a problem like this on the final exam or whatever, that you substitute into the main equation here, guys, is the rotational equation. It combines everything, puts some, everything into one. What I would do is go isolate for T1 here and put it there. Isolate for T2 from here and put it there. And I would isolate for alpha from here and put it there. So please take a minute and do all that and then try to come up with a solution. What I'm asking you is what is the value of A? Yes, Tito. What?
What's the question looking for?
A and T. So now it's actually T's. A equals to what? Acceleration. Yes. Sorry, I can't hear you. Please quiet down for a sec. Let me hear what you're saying.
Is there a friction between the string and the wheel? Not the wheel between
There has to be friction between the string and the wheel for the string to, yeah, but we don't care about that because it's really the tension that's moving the pulley. Okay? The pulley itself is frictionless, but there has to be friction between the string and the wheel. All right, so if you do all that, what I asked you, the acceleration turns out to be A is equal to, anybody? M2G over M1 plus M2 plus I over R squared. I know it's what you got too, right? But you put the R on top. You're a funny man. How did I get that? From the, I showed you all the steps. Plug in, and get A. Do you have something big due these 2 days, couple of days? Yeah. Tonight? What? Do you have anything due today? All right, some common moments of inertia for some of the objects that you'll see in the course. A ring is mr squared as we derived it. We talked about a disk last time, mr squared over 2. We talked about the moment of inertia of a bar, a thin bar. So a thin bar of mass m and length L, where L, please pay attention, is the full length of the bar, is 1/12 ml squared. A sphere is 2/5 mr squared, and a spherical shell is 3/5 or 2/3 mr squared. You don't need to remember these, but it'll be good to your advantage if you do, so you don't have to look them up on the exam. They do take time to look up and stuff. If you know them, then you're good. The moment of inertia of a bar about an axis here, if you recall, we did this last time. That was 1/3 ml squared. How did we get that? From the parallel axis theorem. So you don't need to remember any of this. Parallel axis theorem would be good to remember for sure, because if you have the moment of inertia of an object like that, for example, and you want to find the moment of inertia about an axis parallel to that axis for the same object, you do ICM plus MD squared. I will take us back one more time to the example of a mass at the end of a massless bar. And this is pivoted about point O. And now, last time, we pushed it with a force F. Today, we're going to allow it to move at speed V. I'll give you a minute to copy down those objects, and then please do so and focus here. Yes?
What's the difference between sphere and a spherical shell?
A sphere is a solid sphere. Okay. Like What's a solid sphere example? Like a marble. Marble? Or a ball of gulab jamun? Yeah? Yeah. Right? And the spherical shell will be like a ping pong ball or a ball made out of jalebi, right? Jalebi ball. Okay. So anyhow, a solid marble is a sphere. Spherical shell is like I don't know, a beach ball. Another example, solid ball will be a medicine ball, right? Right? And volleyball will be a spherical shell. All right, guys. So yes. No, I don't have any gulab jamun on me. I wish I did. Yes. What? Pulley. For the pulley, for the example that we did just a second ago, I was given. You didn't have to worry about it because I is given. Okay? It depends on what the pulley is made of. Is it a sphere, cylinder, disc, what, bar? I don't know. Bar wouldn't work. What the heck? What do you want? Yes, you.
Yeah. So the I will ask you is not exactly mass for the pulley, but the equivalent mass in the inertia.
Yes, I over R squared. That's a good way to think about it. That's how I think about it. By the way, that solution there, I did not solve 4 equations for unknowns and put it there. I put it there because I looked at the force acting on the system. What is the force? M2G divided by the equivalent mass of the whole system, the inertia of the whole system. You cannot do that though. All right? Okay, so let's go back to this example, guys. If an object this is connected to the pivot by a massless bar, it is moving down at speed v. What will the bar cause it to do as well? Swing, rotate. So it will have to have angular frequency, angular speed, omega. So the kinetic energy of this mass, K, is equal to 1/2 mv squared. But V also equals to what? Omega R. So plugging that in there, I get that K is equal to 1/2 m omega squared R squared, which is the same as 1/2 m R squared omega squared. And this is the, what guys? The moment of inertia. So the expression of 1/2 mv squared becomes 1/2 I omega squared. Following the same logic that we followed on the lecture on Wednesday, in going from 1 point mass, if you recall, well, then we did 3 point masses spinning at the same speed or angular acceleration. Then we went to the ring. We could follow the same logic that we have followed so far to prove that this holds not only for a point mass, but for any solid object, for any rigid object. And you can prove that by going in succession from point mass to a bunch of point masses to finally, a solid object, which begin with a ring and go on from there. So if it's a point mass, I is mr squared. If it's not a point mass, then I is one of those things there. All right, so example, I have a solid disk and it's pivoted here. This is the pivot. Which way is this sphere going to move if it falls? That's the pivot. What is it going to do? Guys, if the pivot is in the center of mass, it's going to spin. Ravit has an idea. What is it going to do? Flop. It's going to wobble. Right? Flop like that. Can you come and demo, please? Oh, come on. No, that's fine. I have something in mind for you for Wednesday's lecture. You're going to help me then. It's going to be either you or Avi. Hi, Avi. I need somebody small. Small guy would do as well, but usually girls are smaller. I have something I don't want to break, so, don't get scared. And don't you dare not come. Right. So, guys, this is going to wobble, it's going to fall like this. This is the pivot, so I'm not going to write it down. You have a disk pivoted here, it's going to fall like that. Wobble, wobble. Okay? So as it's falling down, I'd like to find the speed of point A. As that falls down, what is the speed of point A at the bottom? So VA equals to what? The bottom. So that sphere, so the whole thing is going to fall like that, okay? So as it's falling down, what is the speed of point A at the bottom?
Angular speed or?
Speed, V. Here, you see the V, Kevin? It's a V, right? What the hell, man? V. There. Take a few minutes to do that. Next week will be a bit intense because we have 4 lectures and 1 help session. I'm going to be busted by the end of it. If you have any energy drinks, bring them my way. I'll be taking some of those. So I'll see you 3 times on Wednesday. Right? Okay, so work of the non-conservative force equals to a change in mechanical energy. All right? So there is no non-conservative force, therefore this is 0. So that's all 0 in this case. Therefore delta K plus delta U is 0, and delta K is negative delta U. Okay, what is delta K in this case? How about I say 1/2 mv squared for A equals to negative into, well, do I gain or lose potential energy? So minus mg times, how much distance does A fall? 4r, given that this is r. Are we good? But that was a rhetorical question. I'm not asking your opinion, really. And it's not what you think. It's not what's in the books and stuff. Yeah, it's a little of that, but you know, yeah. What's up?
Okay, so since like circle actually is moving like goes down, it's not just the topmost point.
Time's up, man. That was taking too long. What?
The answer is square root of AGR.
No. Yes. Yeah. We have an issue, guys. So it's a mass of A, let's say. Well, guys, this is not right. Okay, this is wrong. Why? Because we have, first of all, it's a rotational problem. Okay? The energy that you gain from the falling object goes into rotating not just A, but the whole object. It all moves together. So you have to keep that in mind. This is garbage. This would be fine if what? If there's a massless bar connecting that mass element, it falls down. That's okay. Mass A. This is total rubbish. None of it is true. So this is garbage. What you say then? No, keep it there. Cross it out. 1/2. I about what? I about the pivot at O. Omega squared equals to. Well, that's fine. 1/2. The change in kinetic energy beginning at omega equals 0, going to omega down here, you know. So omega equals 0 here, to omega, some omega down here, our spinning. That's fine. Equals to, guys, now I have to account for the change in potential energy. I could do this in one of 2 ways. I could go and track every bit of mass in this object and say that fell 2r, that fell 4r, that fell 2r, that fell I don't know how much, and keep, or I could keep track. Remember we said about the whole thing, the whole idea behind the center of mass is that I don't want to be able to, I don't want to have to track every little object in the system. All I got to do is look at the system as a whole, right? I could replace this object for the purposes of center of mass, not moment of inertia. I could say that the mass of the object, which is centered here, has fallen by how much? By 2r. So that is equal to, and m is the mass of the disk, right, guys? So, right, we have lost so minus, and we have lost potential energy in the amount of mg times 2r. Okay. So that's fine. That makes sense. The amount of kinetic energy that we gained is equal to the amount of potential energy that we lost, and that's the way it should look. It's a rotational problem. It should be treated rotationally. Now, okay, so next, I could say that 1/2. What is the moment of inertia of a disk? mr squared over 2 times omega squared equals to mg 2r, and we are home free almost. What?
Wasn't that the rotational, sorry, the moment of inertia for a disk rotating about its center?
Too long. What? Was that a statement or a question? It doesn't matter. It's irrelevant. Time has passed.
Add md squared.
What?
Add md squared.
What the hell? That was short, but it's, I don't know. Guys, these two people, we have a problem here. The moment of inertia of a disk about its center of mass is 1/2 mr squared. When it rotates about its center of mass, it's 1/2 mr squared. When it rotates about the pivot at the bottom, what is it? How do you get it? You use the parallel axis theorem. So the moment of inertia is not, okay, what's the mistake? Well, it's not ICM, it's I about O, right? So I about O is not that. Cross that out. I about O is ICM plus the mass of the object times d squared. That's for you because you're asking me about the parallel axis theorem. What does d indicate, guys? D is the distance between the what? The center of mass axis and the axis of what we rotate now. So that is given by how much? R. So that's going to be mr squared over 2 plus m d squared r squared. That's 3/2 mr squared. And that is what should go in there. The 1/2 is 1/2 for kinetic energy. I is 3/2 mr squared. And you get omega squared is equal to plus mg times 4r, 2r. Okay, now we get omega. Okay, fine, we have omega. Omega is the angular speed of this thing. Angular speed of the disk as a whole, right? Is it the same for which point has a higher angular speed here? That one or that one? Same. We talked about that last time because they all cover the same amount of angle, the same amount of time. They have the same omega. Okay. So I go say now VA. Now last bit. Okay. So check. That was our first thing here. That's good, and that's good. Next is VA equals to what? Omega times R. Are we good? Julie, are you paying attention? To me? To my stuff? What are you guys up to? Julia, let's the term. I think I can bring you up here. You're having way too much fun in the back. We will have fun. No, I'm just kidding. I won't bring you up here. Don't feel scared. Okay, are we done? Guys, we get omega. Fine, you get omega, plug it in there, and we're done. Smarty pants there. Are you okay with that or no? Not you, not him, the one behind you. My conscience, the one that keeps correcting me if I want to do evil stuff. Yes. No. Let me talk to the guy first. Well, think quicker. We're out of time. What? Do you want some Red Bull? Red Bull? I don't take it either. Yes. What? No. Because the initial omega is 0, final omega is we're going pretty fast down there. Woo. Yeah? Yes. What the what?
Doesn't omega equal VA over R?
Yes. Yes, Kevin, yes, but that's saying the same thing. People, shut up. That was not cool. What? Yeah. Please pay attention, guys. I've caught you 3 times so far. Except for my conscience there and his buddies. Guys, if an object, pay attention. What is the pivot here? Okay? And what is the mass here? V equals to omega r. What if I call this distance x? Please pay attention. V equals to omega what? X. What if I call this distance 6 Jimbos? Right? That V will be equal to 6 Jimbos times omega. What the hell? Omega. Omega 6. Okay, guys, where is the pivot? Here. How far is A from the pivot? 2 Jimbos. Right? So omega times the distance to the pivot, which is equal to 2 r. Now, hint, hint, the quiz on Monday is going to be different from last week's quiz. Because last week you had a chance, this week, come on guys, it's ups and downs, right? 1 week it's good, 1 week it's better. Right? So, this quiz, you are going to get part marks, but very few of you are going to get full marks. Okay? I could ask you, let me give you a tip, for example, maybe it'll give you a chance to get full marks. What is the angular acceleration of this point? Sorry, what is the total acceleration vector of this point when it's here? Ooh. All right, have a good weekend.